Let us analyze the phenomena of Doppler's effect when source is moving and observer is at rest. Say if this is the source of sound having frequency n0 Hz, and in front of it at some separation an observer is standing which is at rest. It is not moving like in the previous case we have taken when source was at rest and observer was moving. It's if observer is at rest and source is moving with the speed Vs. Now in this situation, the source will emit sound waves which are having wavelength lambda naught, which is c by n naught. So if source is at rest, it will emit a wave which is of wavelength lambda naught, and the wave will travel a distance lambda naught during one oscillation as the wave is propagating at a speed c. Now in this situation, if source is moving with the speed Vs, we can say during one oscillation, the source will also reach some position which is ahead of its initial position. And this distance we can simply call, or we can write the value of this separation as Vs into 1 by n naught, because 1 by n naught is the period of one oscillation, and during one oscillation the source will be displaced by distance speed into time. So when the sound wave will reach this position, which is effectively one wavelength, the source will be located here where it will complete one oscillation. So the wavelength of sound which is emitted in air will be effectively only this, because this is the point which was emitted from the source corresponding to start of an oscillation, and this is the point of wave where source is completing one oscillation, and during one oscillation the source has travelled a distance Vs into 1 by n naught. So this is the wavelength which is emitted from the source, and it will travel further in the medium toward observer. So the wave which is emitting out from the source to the observer will be this, and this wavelength can be written as lambda apparent, or we can write apparent wavelength, apparent or effective wavelength emitted by moving source is this lambda apparent or lambda effective can be written as lambda naught, which is the actual wavelength, minus Vs by n naught. So here lambda naught we can write as c by n naught. So this can be written as c minus Vs by n naught. This is the apparent wavelength, or the wavelength which will be received by the observer. So when the waves are approaching at a speed c and observer is at rest, the number of oscillations received by the observer during 1 second will be that in c meter length only, because here observer is at rest. So in this situation, number of oscillations heard by observer in 1 second, or it can be written as apparent frequency received by observer, can be given as n apparent. This is equals to c by lambda apparent. If we substitute the value of lambda apparent, this will be c by c minus Vs by n naught. So this will give us the apparent frequency to be n naught multiplied by c minus Vs. Here we can also modify this expression. If the source is receding away from the observer, then the effective wavelength of sound emitted by the source will be expanded, and it is more than the actual wavelength. So this can be written as lambda naught plus Vs by n naught. So this will be with positive sign. So in this situation the expression will be modified like this. This is also quite a useful relation. Just you need to keep it in mind for different numerical applications in future.